In this video, we are going to learn about the fundamental theorem of algebra. Now, if a polynomial is of degree n, which is greater than or equal to 1, then the equation p of x equals to 0 has exactly n roots. So meaning where the polynomial is has that many solutions. This includes multiple and complex roots, and I'll explain that in these three examples just below. So for example, these are all quadratic equations or quadratic functions that we're going to find their zeros. And you'll see here, since they're all degree 2, there should be 2 roots for all of them according to the fundamental theorem of algebra. So if I were to solve this equation, I can see that I can just add 4 to both sides, take the square roots of both sides, get the absolute value of x is equal to 2, and I end up getting x is equal to plus or minus 2. So I have two solutions, x equals 2 and x equals negative 2. And you can see that on the graph too, it crosses the x-axis twice. But sometimes you can't get it just from the graph. This one only crosses it once, touches it once, and this one doesn't cross the x-axis at all. But apparently there are still two solutions. So here, if I were to solve this equation, x squared minus 2x plus 1, this is a perfect square trinomial. So I can factor that to be x minus 1 squared, which I can just set x minus 1 equal to 0 and get 1, but it has a multiplicity of 2, since that factor appeared twice. So this says this includes the multiple roots. So even though I just got the equation, the answer only got one unique answer, I did get that answer twice. I got x equals 1 twice. That's a solution. And lastly, this one doesn't cross it at all, but if I try to go solve it, I can use complete the square to solve this. So x squared plus 2x equals negative 2. I can add a number to each side to make it a perfect squared trinomial on the left, which is 1. That's half of 2 squared. And I end up getting a perfect square trinomial, which will be x plus 1 squared, which looks very similar to the expression on the left, is equal to negative 1. I can take the square roots, get absolute value of x plus 1 is equal to I. So then x plus 1 equals plus or minus I. So my two solutions will be x equals negative 1 plus or minus I. So those are my two solutions. Those are complex roots. So see, they all had 2 no matter what because of the degree at the top. Now the way this idea works is that if there are n roots, you can write a factored polynomial with n linear factors, meaning x minus a number. So right here, with x equals 2 and x equals negative 2, I can write y is equal to x minus 2 times x plus 2. Over here, since I got 1 with a multiplicity of 2, I can write y is equal to x minus 1 times x minus 1. And over here, I can write y is equal to x minus negative 1 plus I times x minus negative 1 minus I. So two factors, but if you look here, whenever you multiply them out, you'll always end up with x squared, because it's just like x times x for that leading term for all of them, x times x. So if I had n of these, x times x times x n times, I'll end with x to the nth power, and that's the degree of the polynomial. Now let's put this into practice. So we see here we have a quintic polynomial, so I'm already expecting that I should have 5 roots no matter what. So what I'm going to do is list out the possible rational roots to start so I can try to find a few. So looking at the leading coefficient, the factors of 1 is just 1. If I put LC for leading coefficient, and then for my constant term, CT, my factors are 1, 2, and 4. So my possible rational roots, so possible rational roots would be my constant term factors over my leading coefficient factors. So 1 over 1, 2 over 1, and 4 over 1. So just 1, 2, and 4. So I have 6 possible root combinations to try out. And I'm going to try out positive 1 first and just use synthetic division to see if it works. So let's test out 1 as a possible root. So that comes from the factor x minus 1. I'm going to divide into this polynomial using its coefficients 1, negative 3, 3, negative 4, and 4. I can bring down that leading coefficient. 1 times 1 is 1, negative 1 plus 1 is 0, 1 times 0 is 0, negative 3 plus 0 is negative 3, 1 times negative 3 is negative 3, 3 plus negative 3 is 0, 1 times 0 is 0, negative 4 plus 0 is negative 4, 1 times negative 4 is negative 4, 4 plus negative 4 is 0. So now, since I got a 0 for the remainder, 1 is definitely one of the roots, and I can actually factor by writing x minus 1 times the polynomial I got after I divided it out, which, starting 1 less power, would be 1x to the 4th minus 3x squared minus 4 is equal to 0. And I can set both of these factors equal to 0 and continue to solve. So I'll have x minus 1 equals 0, which gives me x equals 1, which I already tested is correct. And then I'll have x to the 4th minus 3x squared minus 4 equals 0. And now I want to factor this quadratic, which I can do using substitution. I could substitute out x squared for a. So I have a squared minus 3a minus 4 equals 0. This factors into a minus 4 times a plus 1. And then I can go right back and replace a with x squared. And that means that this quadratic factors into x squared minus 4 times x squared plus 1. And then x squared minus 4 can factor into x plus 2 times x minus 2. And even x squared plus 1 can factor using complex conjugates. That's the sum of squares. Into x plus I and x minus I. Lead me to set all of these equal to 0. So my other solutions would be x equals negative 2, x equals 2, x equals negative I, and x equals I. So all of my solutions are 1, negative 2, 2, negative I, and I, which are 5 solutions, which I expected because of the fundamental theorem of algebra tells me there are 5 solutions. It's a great way to know if you're finished solving a problem or not is if the number of answers matches the degree. So let's try this out with another example. This one you need to start off by getting it equal to 0, or else you cannot use the fundamental theorem of algebra to predict how many solutions you have. So we'll add everything to the left. We'll give it as x to the 5th plus 5x to the 4th plus 4x to the 3rd minus 10x squared equals 0. So I can already see here that this is a 5th degree polynomial, so I should have 5 roots. So I'm going to start by factoring. I can see that every term has an x squared as a common factor, so I can start by factoring that out, leaving me with x squared times x to the 3rd plus 5x squared plus 4x minus 10. Now if I try to factor by grouping, I'll end up with x plus 5 after taking out an x squared, and 2x minus 5 after factoring out a 2, which aren't a similar factor. So factoring by grouping will not work for this cubic polynomial. So I'm going to have to go through a very similar tactic. I need to write out all the possible rational roots. Which my leading coefficient factors are just 1, and all the constant term factors are 1, 2, 5, and 10. Now we put all of those over 1, so these would be the possible rational roots. So I need to test these out to see which one could work. And again, I'm going to start by just trying out 1 to begin. So right now, I'm trying to solve the equation x to the third plus 5x squared plus 4x minus 10 is equal to 0. Because I already know I'm setting x squared equal to 0 later. But I'm going to divide out that 1. So it's like 1, use the coefficients from my right factor here, 1, 5, 4, and negative 10. I'm hoping I'm going to get a remainder of 0. So drop the 1. 1 times 1 is 1. 5 plus 1 is 6. 1 times 6 is 6. 4 plus 6 is 10. 1 times 10 is 10. And negative 10 plus 10 is 0. So 1 is a root of my polynomial, which comes from the factor x minus 1. So I can factor this to be x minus 1 times x squared. Again, 1 less power from what you started with, plus 6x plus 10. And now I can set both of those factors equal to 0. So x minus 1 equals 0, and x squared plus 6x plus 10 is equal to 0. And now I can solve these 3 equations. The top equation is just x equals 0, but that factor does appear twice. So it does have a multiplicity of 2. It's a good thing to keep in mind. The other one just solves for 1, and only one of those factors. And over here, this cannot factor. No two numbers multiply to 10 and add to 6. So I'll have to use a different solving technique, which I'll solve by completing the square. So what number do I need to add to make this a perfect square trinomial on the left? Half of 6 squared would be 3 squared, which is 9. I'll add that to both sides, giving me x plus 3 squared is equal to negative 1. I'll take the square root, and I'll get absolute value of x plus 3 is equal to I. So it gives me x plus 3 is equal to plus or minus I when I get rid of the absolute value. And I'll subtract 3 to get negative 3 plus or minus I. So my last two roots are negative 3 plus I and negative 3 minus I. So if you were to try just to look at a graph, you would have only seen 2 zeros, but one of them would have been a multiple 0, which counts for 2. And the other 2 would have been a complex conjugate pair of solutions, which counts for another 2. So there are 1, 2, 3, 4, 5 roots to this polynomial equation. And that is the fundamental theorem of algebra.